So for the example, it says, an object is sent through the air. Its height is modeled by the function h of t equals negative 5t squared plus 3t plus 65, where h of t is the height of the object in meters and t is the time in seconds. So we're looking at height versus time. And then it says, estimate the rate of change in the object's height at 3 seconds. So when you're looking at a problem like this, it doesn't indicate whether you're looking at IROC or IROC. But the indication to me that this is an IROC problem is that it's telling you to find the rate of change at one particular time. So this isn't at a particular instant. So that's how I know that I'm looking at an instantaneous rate of change, or an IROC. Okay? So what we're going to do is set up a chart. And this is just going to help us organize our average rates of change over smaller and smaller intervals. So we're going to set up a chart, and what we're going to do is calculate the average rate of change over small intervals. So we'll start with a larger interval, and then we'll make it smaller and smaller so that it gets closer to the point at t equal to 3 seconds. Okay? 3 will always be used as one of our endpoints in this case because we're looking at the instantaneous rate of change at 3 seconds. And then we can estimate the instantaneous rate of change depending on what the values of the average rates of change are approaching. Okay, so here I've already sort of set up my interval chart, and I've sketched the function as well on the right hand side. So we're looking at time versus height. And so I could have ignored the left side of the graph here on the left on the left hand side of the where the negative time values are, where the negative time values are, I could have ignored it, but I just sort of sketched it so you can see what the parabola looks like. And so the intervals I'm going to choose, what I'm going to start by doing is looking at the intervals on the right hand side, so average rate of change on the right hand side of the point, and then I'll look at average rates of change on the left hand side of the point as well. So I'll make my intervals. So I'll start at 3, and I'll continue to a point that's 0.1 units away from it, so I'll go up to 3.1. And then I'll set up another interval where the interval actually gets smaller. So 3 again will be one of my endpoints. So that'll be my starting point. And this can continue up to 3.01. And you can do a third interval as well if you want, between 3 and 3.001. So you're getting closer and closer to the actual point. This is sufficient as well. Okay, so this is the interval that would be getting close to the IROC from the right hand side. I'm going to do the same thing on the left hand side. So this time, instead of being 3 being my starting point, it'll end up being my ending point. And we'll talk about what our starting point can be. Okay, and so first I'm going to have a point that's 0.1 units away from 3, so that would make it 2.9. And then I'll have a point that's 0.01 units away from 3, so that would be 2.99. Okay, and so there's my intervals with it approaching it from the right hand side and then approaching it from the left hand side. Okay, so at the top of the chart that I have here, you'll also notice that I've written h of t1 and h of t2. So what this will help me do is sort of organize what the height of the function would be at the first time, and then the height of the function would be at the second time. And then using these values, I can find the slope, or the average rate of change. So this is actually the average rate of change. And so I'll find the change in height over the change in time to help me figure out what the average rate of change is in that particular interval. Okay, so for the height at the first time, all I need to do is plug in 3 into the function up here. So I just have to find h of 3. And if I do that on the calculator, I get a value of exactly 29. And this makes it a little bit easier because I don't need to recalculate it for t equal to 3 because I already know the value is going to be 29. So my initial point here, the initial height will be at 29. And I can also use this value again as the end point here because it's the exact same value of t, so it'll be the exact same height. So this will also be 29, and this will also be 29. Just makes it work a little bit easier. Okay, now I have to find the height of the function at the second time, so I'm just going to plug in 3.1 on my calculator in this function. So negative 5 times 3.1 squared plus 3 times 3.1 plus 65. And when I do that calculation, I get 26.25. And I usually find that it's easiest to do all your calculations first and then to figure out the average rate of change after. Okay, and if I do the same thing for 3.01, plug it into the function, I get 28.7295. Okay, and then we'll do the same thing for 2.9 and 2.99. So if I plug in 2.9 into the function, I get 31.65. And when I plug in 2.99 into the function, I get 29.2695. So it's the same idea as average rate of change, except I'm not showing all my work. Instead, I'm just showing my end results in a table. Okay, now to find the average rate of change at each of these intervals. So I'll start with the right hand side ones, and then I'll do the left hand side ones after. So to find the average rate of change, I'll find the change in height, so find the difference between these 2 points, and then the change in time, so I'll find the difference between these 2 points. Make sure that you're doing h of t2 minus h of t1 divided by t2 minus t1. So it's the exact same slope formula. Okay, so when I do that, what I get is negative 27.5 for the first one. So that's the average rate of change in that particular interval. So if I look at the interval that's even closer to t equal to 3, and I do the change in height over the change in time, I get negative 27.05. So you can see that the values have changed slightly. Now, what I'm going to compare is this value here, which is a smaller interval, to the value that I get when I approach the that particular point from the left-hand side. So again, I'm going to do the same thing. I'll find the change in height over the change in time. And in this case, I get negative 26.5 for the first interval. So that's the one that's a little bit larger. And then I'll do the same thing again. Change in height over change in time. And I get negative 26.95. So this is the smaller interval from the left, and that's a smaller interval from the right. And you can see that the average rate of change is sort of approaching a similar value. And in this case, you can see that the average rate of change is sort of approaching negative 27. Okay? So going back to the question, it says estimate the rate of change in the object's height at 3 seconds. And so we can estimate the instantaneous rate of change to be approximately negative 27. Okay? And the fact that this is negative indicates that the graph must be decreasing at that particular point. And the 27 indicates that that's the change in height over time. Okay, so the rate of change would be 27 meters per second coming downwards, or negative 27 meters per second. So therefore, to answer the question, the rate of change at 3 seconds is about negative 27 meters per second. Okay, so that means that at that particular instant, the height of the object is decreasing 27 meters in 1 second. Okay, and that's how you calculate instantaneous rate of change.